The electromagnetic coupling of time-dependent electric and magnetic fields can be demonstrated with this transformer circuit that also includes a current-sensing resistor on the primary coil. On the primary side, a signal generator creates an input sinusoidal voltage signal that sends a current I of t into the primary coil with N1 windings. On the output side of the coil there is a resistor Rs across which the current can be sensed. This is achieved by measuring the voltage Vrs across this resistor and using Ohm's law to determine the associated current. The time dependence of current I creates a magnetic field in the primary coil that is enhanced through the ferrite filling of that coil. In this case, the ferrite filling has a toroidal geometry. The time-dependent magnetic field inside the ferrite then induces, according to Faraday's law, an electric field in the secondary coil. The secondary coil has N2 windings, and the time dependence of the electric field in this coil can be sensed by detecting the voltage V2 across its ends. The photo shows some of the materials used in this particular setup. The outer diameter of the violet toroid, that is made of ferrite material classified as 4C65, is about 24 millimeters. The colored coating identifies the ferrite material inside of the toroid and aids in maintaining mechanical integrity. The black appearance of the ferrite material is apparent from a similar toroid that is shown above the violet one that is used here. A 1 ohm resistor used for the current sensing in the primary circuit and enameled copper wire are also shown. The material classification 4C65 indicates that the initial relative permeability μR is at room temperature 125. Successful experimentation should confirm this value for the relative permeability. The graph on the bottom right shows that the relative permeability increases significantly with rising temperature, and at temperatures above 300 degrees Celsius can attain values in excess of 250. The photos show two possible realizations of this transformer circuit. A lab bench setup is shown on the left, and a setup using a computer interface is shown on the right. As it is good practice, the two coils are wound all around the ferrite toroid and overlap. In order to avoid floating voltages, a common ground is established in both circuits. On the left, a sinusoidal AC voltage is applied at 50 kHz. The time-dependent current in the primary circuit is sensed by measuring the voltage across the resistor. The electromagnetic coupling in the transformer circuit then creates a voltage signal in the secondary circuit that is time-shifted by 90 degrees. The setup is shown here once more. The physics in the primary coil is described by Ampere's law. Namely, the magnetic field strength is equal to current density J plus the time change of the electric flux density D. In coil 2, Faraday's law applies. The curl of the electric field strength is equal to the negative time differentiation of the magnetic flux density B. These are the two Maxwell equations that describe the electromagnetic coupling. The Maxwell term in Ampere's law, dD on dt, does not need to be considered because the electric field in the long wire of the primary coil is extremely weak. The current I in the primary coil that depends sinusoidally on time creates a sinusoidal curling magnetic field with a strength H in the primary coil. The right-hand rule confirms that the circulation of the magnetic field lines of the magnetic field for the current direction indicated is anticlockwise. This is consistent with the fourth Maxwell equation, Ampere's law, since the current in the primary circuit is equal to the current density times the cross-sectional area of the enameled copper wire. Similar to what happens in an electric capacitor, the ferrite material inside the primary coil enhances the magnetic field. The material classified as 4C65 combines iron and nickel and belongs to the class of ferrimagnetic materials that can be magnetized, however their magnetization is not permanent. As illustrated on the top right, for an external magnetic field of B equals 0, the elementary magnets in the ferrimagnet are randomly oriented. However, they tend to align with an external magnetic field, so as soon as B becomes larger than 0, they point in the same direction as B. The capacity of a ferrimagnetic material to be magnetized is measured by the parameter relative magnetic permeability μr, which is measured in this experiment. μr is therefore the constitutive parameter of that material. For the toroidal geometry considered here, the elementary magnets align in a circular sense, as shown at the bottom right. Ferrite materials are porous materials. That means they are not homogeneous but heterogeneous, and they are affected by voids and grain boundaries. This is apparent from the electron micrograph shown on this slide for a ferrite that has a porosity of 0.05. Porosity can be determined from the ratio of the ideal density of the homogeneous crystal divided by the measured density. In order to compare measured permeabilities, it is important to consider the porosity. For example, for the material considered here, which is a 50-50 nickel-zinc ferrite, an initial permeability of 240 is quoted for a porosity of 0.15. These values and the micrograph are from a standard on ferrites from 1959 by Smead and Wine. The figure at the center, also from this book, figure 47.2, shows the dependence of the initial permeability, quoted here μ0, as a function of porosity, for nickel ferrite and also nickel zinc ferrite. It is apparent that over this range of porosity, the permeability changes from 20 all the way up to 500. The micrograph also indicates the size of the crystallites of the polycrystalline material. It is well known that permeability also depends on the crystal size. Porosity and crystal size are the two main reasons why permeability can vary drastically for a certain type of ferrite. It is therefore not surprising that the technical specifications for the toroid considered here specify a value of 125 for the initial permeability, which is significantly lower than the value of 240, which is quoted in this standard book on ferrites. The value of the relative permeability μr determines the magnitude of the magnetization of the ferrite core by the time-dependent magnetic field strength H created by the primary coil. As the electric current I in the primary coil, the external magnetic field strength H, also the magnetic flux density in the toroid core is sinusoidally dependent on time. This time-dependent magnetic flux in the toroid creates a circular electric field in the secondary coil. The electric field in the secondary coil is also time-dependent. Because of the time differentiation in Faraday's law, the time dependence is a cosine function. The current in the primary coil and the voltage in the secondary coil are therefore time-shifted by 90 degrees. The electromagnetic coupling in this transformer setup can be experimentally verified by sensing the current in the primary circuit using a sensing resistor Rs. Across this resistor Rs, according to Ohm's law, the current I of t is measured as Vrs on the resistance Rs. If the input voltage varies sinusoidally, the current I of t, the voltage Rs across the sensing resistor, and also the magnetic field strength H in the primary coil vary sinusoidally. Looking at the primary coil from the top, we might assume that the current going through the turns might come towards us on the left of the core and go into the plane on the right of the core. We can then relate this current I of t to the magnetic field strength in the core, H of t, by defining a closed Amperian contour. A sensible choice is a rectangle whereby we go in the core upward, then to the right and then downward on the outside, and back at the bottom. With such a virtual closed path, we can apply Ampere's circuital law. In the illustration shown, the path encloses 4 turns of wire. The right-hand side of the circuital law, which is the area integration over the current density, is therefore equal to the current that passes through 4 turns of wire. The magnetic field strength H associated with this enclosed current can be worked out by looking at the 4 sections of the path. On the outside of the primary coil on the right, the magnetic field is weak. Therefore, the contribution to the integral by that section of path may be approximated to 0. Along the 2 horizontal sections of path, the magnetic field is perpendicular to the path element. The contributions from these 2 sections are therefore 0. The only section of the path that contributes significantly to the integration is the section that is inside the core. Because of the symmetry of the arrangement, the field direction is here either upward or downward, and the magnetic field is always aligned with the path. The left-hand side of Ampere's circuital law is therefore exactly equal to what we are interested in, the magnetic field strength H inside the core. It is equal to n times the current I of t, whereby n is the number of turns per length unit. The result can be readily applied to a toroid. In this case, we might have a total number of windings of turns, n1, so that, assuming uniform winding, n, the number of turns per length unit, is equal to n1 divided by 2 pi r, where r is the mean radius of the toroid, and therefore 2 pi r the mean circumference. The relationship between the sinusoidally changing magnetic field strength H and the current I is therefore H equals N1I divided by 2 pi r. Combining Ampere's law as it applies to the toroid with the result that we obtain from Ohm's law, we see that the magnetic field strength H inside the core depends on the number of windings N1, the mean circumference of the toroid 2 pi r, the sensing resistance Rs, and that it is proportional to the voltage across the sensing resistor Vrs. Both H of t and Vrs of t are sinusoidal. Applying now also the constitutive relationship, we find that the flux density B of t, also sinusoidal, is given by mu naught, mu r, n1 times Vrs divided by 2 pi r times Rs. It is clear that now the parameter mu r, that describes the material properties of the core, can be determined if the magnetic flux density B can be measured, since on the right-hand side of the equation all quantities are measurable. The B of t in the core can be determined if a secondary coil is wound around it and Faraday's law applied. Faraday's law states that the change with time of B will induce an opposing electric field in the coiled wire. In order to take advantage of this, one has to convert the differential form of Faraday's law into its integral form. Importantly, the induced electric field in the secondary coil is a second manifestation of electromagnetic coupling in this setup. It may also be noted that the time differentiation in Faraday's law turns the sinusoidal time dependence into a negative cosinusoidal dependence for the electric field in the secondary coil. Let us consider a single turn of the secondary coil. Such a single winding then defines a cross-sectional area A of the core. The wire defines a closed path around it. The differential form of Faraday's law can be converted into the integral form using Stokes' theorem. The closed path that is defined by the single winding then appears on the left-hand side of this equation, and the area defined by it on the right-hand side. Furthermore, the left-hand side equals the potential difference for one winding, and the right-hand side is the change with time of the magnetic flux through the area defined by it. The determination of the magnetic flux in the core is therefore facilitated via a voltage measurement on the secondary coil. In order to apply Faraday's law, we need to differentiate the equation for magnetic flux density B on both sides with respect to T. This gives the equation at the top. Then we substitute the left-hand side with the help of Faraday's law and obtain minus V of T on N2 times A. The minus sign is due to Lenz's rule. In the blue frame, we now have an equation that contains only measurable parameters and the quantity μr that we want to determine. N2 is the number of windings of the secondary coil. The equation relates the voltage measured across the secondary circuit with the voltage measured across the sensing resistor. This sinusoidal voltage, however, has to be differentiated. The differentiation with respect to time of the sinusoidal voltage VRS across the sensing resistor is detailed in the red frame. We obtain the amplitude VRS naught times the cosine function of 2 pi f times t times 2 pi f. 2 pi times the frequency f is equal to the angular frequency in the argument of the sine function. The factor 2 pi f on the right-hand side of the equation comes about because of the application of the chain rule in the differentiation. We can now substitute with this expression in the blue frame, and since this equation is valid for every time t, we might choose a convenient time, namely one of the times where the cosine function is unity. At those times we can replace the voltage functions with their respective amplitudes VRS naught and V naught. Working now with the two voltage amplitudes and rearranging the equation shows that the relative permeability of the core can be determined from the equation displayed here. In particular, the frequency f of the electromagnetic coupling and the ratio of the two voltage amplitudes in the primary and secondary coil respectively have to be known. The graph at the bottom right shows the two important voltage signals as a function of time. If VRS is assumed to be sinusoidal, then the voltage signal across the secondary coil is phase shifted by 90 degrees to the right. The first differentiation with respect to time of VRS is therefore in antiphase with V of t, as it is indicated by the red dashed line. This circuit simulation models the transformer setup that can determine the relative permeability of a ferrite core. On the left, a 1 kHz sinusoidal voltage signal is generated with an amplitude of 500 millivolts. The inductance of the coils at the center is assumed to be 0.27 millihenry. The oscilloscope that models the secondary circuit on the right has an input impedance of 1 megaohm that is simulated via a 1 megaohm resistor. The oscilloscope on the left shows the voltage across the sensing resistor RS in green, and in phase with that, in yellow, the current that passes through this resistor. The oscilloscope on the right shows the voltage signal across the secondary circuit. The vertical gray bars give time references. It can be seen that the signal on the right is phase shifted with respect to the signal on the left by 90 degrees, as it is expected. The respective maximum voltages are displayed and could be fed into the equation on the previous slide in order to work out the relative permeability μr for this situation. It may be noted that the voltage measured across the resistor in the secondary circuit on the right is effectively equal to the 500 millivolts generated in the primary circuit. This is because the transformer modeled here has equal number of turns in both coils. Benchtop setup of the experiment. At the bottom there is some wire, the resistor, and also two toroids. The purple toroid is set up on a breadboard with the resistor in the primary circuit shown here. 50 wires have been wound for both coils, and a common ground has been created here. At the moment, a frequency of 10 kHz is fed into the primary circuit, and the oscilloscope shows two voltage signals. This one is the primary circuit voltage signal, which has a significant amount of noise on it, whereas the other signal is the voltage across the secondary coil. Using the measurement option of the oscilloscope, the peak-to-peak results for those voltages can be measured. At the moment, channel 1 has a peak-to-peak of 5.9 millivolts, whereas channel 2 shows 656 millivolts. The frequency is 10 kilohertz. By changing the amplitude, one can vary the voltage outputs of both coils, and it's apparent that the voltages are proportional to each other. Very low settings, and this is a high voltage signal. This is an excerpt from a lab book record for a measurement like this. At a frequency of 50 kHz, 6 pairs of voltages were recorded and then graphed. Finally, the relative permeability of the toroid was derived. The table shows measurements for VRS in millivolts and with an uncertainty of plus minus 4 millivolts. In contrast, the voltages recorded across the secondary coil, V0, have an uncertainty that is insignificant. They are given in volts. The graph shows V versus VRS, and it can be seen that the 6 data points follow a linear trend. The data have been fitted with a straight line, and a slope of 60.5 has been determined. Maximum and minimum estimates for this slope have also been carried out. Substitution of the appropriate parameters in the equation derived earlier gives a relative permeability of 112 with uncertainty margins of plus 20 and minus 10. This agrees with the technical specification for this material of 125 plus minus 20%. It is well known that ferrites such as the nickel-zinc ferrite, for which results were obtained, are affected considerably by porosity. This can be explored by weighing. A typical result is shown here. Assuming a density of 5,330 kilograms per cubic meter for homogeneous material, measurement gives an actual density of 3,720 kilograms per cubic meter. The porosity is therefore about 43%. Adjusting the measured relative permeability of 112 for this effect gives the result of 160 with an upper margin of error of 30. Both values agree generally with the literature values shown in the diagram on the left. However, good agreement is not achieved. Since permeability also depends on the grain size of the polycrystalline material, the remaining discrepancies could be due to that. Furthermore, there could be impurities at grain boundaries. The diagram also shows that the permeability of the material depends strongly on stoichiometry. Replacing the zinc with nickel gives a much reduced relative permeability. It is clear that the permeability depends on the material and its properties, and also its synthesis in a complex fashion. Nevertheless, the material can be readily employed to demonstrate the coupling of the electric and magnetic fields.